this lecture. Part 1 covered a lot of information leakage and specific things about .NET, the do's and don'ts, things that hackers currently are looking at or using in different various ways to try to gain access to your system. Part 2, we're going to look at more from a developer's perspective of things that people are doing in their .NET applications that people have done for years. And with .NET, there's so much new ability and new technology and different ways to use that technology to make your things more secure that people aren't using. They just aren't doing it. And so I'm going to sit here and kind of kick the bucket and try to get people to realize what's potentially useful. Now, you will notice that the slides, I do have a little bit updated slides that will be available online after the convention. So, but they do follow almost perfectly with what you do have in your paperwork. So if you get to a slide and you're like, okay, we're supposed to be on page 1 and he's not there yet, just stay there because you'll see that we eventually get to that eventually. Okay, so we have applications exposed. You can easily embrace some specific .NET functionality, and you can actually sandbox and make your .NET applications very secure, and at least in some situations, you can keep your data from being lost should someone get that zero-day exploit and bust in to your system. Intrusion reaction times play a big role. In any time that your system is actually exploited, assuming you have a nice .NET application on there, a lot of information you don't want to be lost, how do you know that someone is there? How long does it take for you to figure that out? And at that point in time, how much information has the hacker gained? And if the hacker gains that, how much time is it going to take for him or her to brute force your cryptography, et cetera, to get at your information? It is assumed through this entire presentation that you are going to notice the hacker is there at some point in time. Obviously, if you do not ever see the person there, no matter what you do that I propose you do here today is probably going to matter, because they'll have time to reverse engineer all your code, and by that matter, break everything down, find your keys, and then actually be able to exploit, brute force all your cryptographically secure data pretty straightforward. .NET, because of some really good performance issues and its ease of coding, it's really easy to add forensic data, to audit a lot of different things at a lot of different times. The more information you do log, obviously, the easier it is for someone, should those logs be remain there, assuming a hacker doesn't immediately delete them, one can determine the stability of those logs and then actually have something that they can look back on, say whether it's IP addresses, MAC addresses, usernames, etc. The more that you log in your application will definitely help you look back should you be able to grab those and do something about it. One of the problems with forensical data is that the moment you get onto a system you know has been exploited, the question is, what of the data that is there is actually true? What if it is real? Did a hacker just create this to lead me down this path, etc.? And using a specific type of audit log structure, you can actually use cryptography to ensure your logs are in some way are safe. Now, again, if the hacker just deletes them, then yeah, that's gone. And if your audit log is missing, maybe that's a clue there's a hacker there. In almost all cases, you can know when hackers are on your system. Because in just the case of logs, if the logs are still there and they haven't been tampered with, which you can detect, then you can probably look at them and say, oh, what is going on in my system? A hacker is going to want to change that because that information itself will tell you a hacker is there, and the absence or corruptibility of those files will also tell you that a hacker is there. So basically, with any application that you write, you will have your logic flowing through your application, the code you write, and you will have an if statement. And that if statement will say, if this username this person has entered is greater than 32 characters, then, ooh, that's a problem. This is an attempt to buffer overflow. Logically, It just means that the username's too big. But how many people here actually have a client side, whether it's validator or in the case of a TCP application, you're going to have internal code. How many people here would check on the client side to say, wait a minute, we should probably limit this person to 32 characters before he even sends it? Does that make sense? You're going to logically perform that action. So the only time you would actually receive a username that is outside of the bounds of your application, you're going to, inside of your nice string-len function, you're going to notice that. Functionality failures in a network world should be deemed exposures. Every time you have a functional requirement that says, we need to check and make sure the username's no larger than 32 characters, we're trying to avoid a buffer overflow, or just in the case of .NET, we don't have that problem, the buffer overflow, but we know we can't store anything more than that in our database. You have a functional requirement. When that fails, it is now, a security situation has happened, because only a hacker is going to bypass your functional constraints to try to do something awkward. So all of your failure cases for your logical data comparisons and things that come from a network, come from a database, all of that type of validation, you should obviously log the failures, log who it's coming from, the user information, etc. So just functional failures can lead you to great forensical data. Okay, this last statement is kind of an interesting question. Most .NET developers that I do know use the same mechanisms that they used back in the day. They don't actually try to improve the security in their application, even though they have all of these great new classes and architecture to do so. So the question is, why isn't it actually used? And I don't know. I'm sure any corporation, you're going to calculate the risk, financial reasons why you may do or not do something, and the performance reasons. And these might be constraints that you cannot deal with. You can't add that extra level of cryptography because you just can't. You don't have the performance. In the case of security and losing security for those, be sure that someone makes that business decision, and probably, hopefully, it's not you. Because if someone actually exploits the system using something that we could have secured that, you're going to feel bad. And usually in those situations, should a bunch of credit cards or something get lost, there's generally going to be someone who's going to take the blame, and you don't want it to be you. So the 4 topics that I've decided to cover today: authentication systems. I know everyone here has probably heard other talks about bypassing this authentication or bypassing that. My perspective in this talk on this is everyone's using the same authentication systems we've always used. There's information leakage problems there. And with .NET, we have the ability to increase the security when you start using things like the challenge and response method, because we can use much larger bit hashing, much larger bit cryptography. And going from a 128-bit hash to a 512-byte hash is the difference of 2 lines of code in .NET. A different declaration of the object, and then actually saying compute this hash with that object. So authentication systems. Everyone still uses usernames and passwords. Publicly usable systems are enumeration functions. I've seen advertisements for specific, I won't name names, but for specific dial-up ISPs that if you go to the registration page, you'll see that you can register all your credit card information, etc., without even being over an SSL tunnel. There is just not enough awareness that is being put out there. There's not enough demand by the public and community to go to these places and say, we will not use your application because you don't have these levels of security. So the standard information leakage, obviously most places have finally learned this solution. If someone enters their username and password incorrectly, whichever one may be incorrect, you say username and or password are invalid. I've given this example 1,000 times, but I still think that people need to remember that any time that you are actually authenticating or doing any function where you allow the anonymous user, before he has authenticated, to access those systems, you're just giving them a function by which they can continually request and get information. A good example of one possible solution to these cases are, if you look at like network solutions and different corporations that have like a whois or these different type of functions online, they make it so that people cannot automate attacks or automate enumerations or even use their functionality inside of your product by making it so that they have a bitmap, an actual graphic, where they put a word in here, and after you go to the site, you have to enter that word specifically like that. And it's different for every session that's created, and it's random. In this case, someone can actually automate attacks because you have something different there every time. Have people seen that? A few people. Okay. So enumeration functions, the ability on the network to actually get information. Usernames for people making new applications. It's very simple. Username should be alphanumeric. Give them a decent space. We can do that. Allow no possible other characters whatsoever. This will just make other things easier. In fact, almost all of your text fields, if you can, make it so that it's always alphanumeric. That's why you don't have to worry about validation. It's really easy to validate. You don't have to worry about client-side scripting, SQL injections, all these other things. Usernames should not be email addresses. They should not be anything by which information, especially if you're authenticating before you create your cryptographic session, that's information leakage that's on the network that people are going to see. .NET Forms authentication, basically just a nice, easy wrapper. So if you're creating a .NET web application, you have a nice built-in way to authenticate. A forms token is actually stored with the client after they authenticate, and this magic token is passed back and forth every time you go. So in essence, you're getting authentication on every request, which that's a good thing. You need to do that. But at the same time, it's just a token, like a hash, username hash or something that's going across the wire all the time. This just goes to show that we need to always establish cryptographic sessions before we do authentication. Now, after you actually perform that cryptographic tunnel, you establish that, one would hope that a hacker who then sees all this encrypted data, he can't immediately decrypt that. In the case that he could, obviously SSL and everything we're trying to protect becomes completely useless. We might as well not even use it and get the performance increase and just cross our fingers. So we put a lot of trust in SSL or any type of cryptographic tunnel to do that for us. If we assume that a user has authenticated to the system once, established an SSL connection during that, then things like continually authenticating within that SSL session may simply be more processing that you don't need to do. Or you're putting trust in the SSL session to keep things secure. The SSL session and the session ID that the person have should be linked together so that you can't actually use someone else's session ID in a different SSL, or their session ID, HTTP session ID, in a different SSL session. That alone is enough cryptographically to keep that session secure, assuming we don't have a man-in-the-middle attack. So specific these forms of authentication, the .NET Forms authentication, albeit sure it's a nice add-on, potentially it can help stop replay attack, but this is all assuming that a hacker can brute force SSL, because you should have an encrypted tunnel. Also, this form authentication token can be stolen from the client machine, as perchance also could the SSL key that's being used for that session, etc. Generally, your application, whether it's TCP-based or a web app, should always assume that a client is the hacker. So anytime that someone gives you information, sure, you have to validate it. Sure, you have to validate against least privilege. No, you can't go to this database because you don't have the authorization to do so. However, if someone does give your app the right credentials, you will always accept them. You have to. If you didn't, well then, you'd be denying service to all your users. So using .NET Forms authentication right off the bat, it may be nice because you can just link it in and have your field, and maybe it's ease of use for development, but it itself is not going to specifically make your app secure. So remember that you still have to have your cryptographic sessions, etc. Okay, challenge and response. Challenge and response simply works this way. A server gives you a piece of data. This piece of data is seen by everybody. So assume the hacker has it. You are going to enter your password on the client side. You're going to hash your password. So you have your hash password and this piece of arbitrary data that the server gives you. You encrypt that piece of data with your password hash. So you're using your password hash as a key, and you send the encrypted data across the wire. Assume the hacker sees that as well. Now the hacker has the piece of data that was supposed to be encrypted and your encrypted data. At that point, they can perform what's called a known text attack. They know what's inside, and they have the encrypted version. So from cryptanalysis, it's actually a lot better to have a known text attack than be taking encrypted data, even should you know the algorithm, and just try to decrypt it or brute force it with that. So challenge and response has the ability to be known text attack, but it is a very secure method of performing authentication. Now, when we look at brute forcing, let's assume someone's actually going to sniff this, perform a known text brute force attack on that. The question of how secure is that is not based on the challenge response method, but on, well, which encryption algorithm did you use and which hashing function did you use to actually hash the data and encrypt it. So challenge and response, you can say, I'm using a challenge and response method, which many people do, and then they look down and a hacker gets on there and says, yeah, but it's a 64-bit encryption or 64-bit hash and then encryption. So it doesn't matter. You can do challenge and response all day. So with .NET, you have the ability to do 512-bit hashes easily. It's just a couple lines of code. You have the ability to do 256-bit AES symmetrical encryption. Both of these are fast. And you should buff up your challenge and response authentication systems accordingly. So if you're using .NET. Okay, passwords changed, publicly usable systems. Most people don't actually go back to, say, Sports Illustrated or all these generic places and change their password within a given amount of time. So if you assume for a second that you're using challenge and response, so you perform your authentication, a hacker sniffs that data, it's going to take the hacker, say, 2 months to brute force that and get the password. You're probably not going to change your password on xfoo place because maybe you don't really even care about it because it's just a generically publicly used system. You probably won't change your password there ever. Most people do not. Perchance, if you're paranoid, you might change it every couple months, but most likely a hacker is easily going to be able to brute force that before you change it again, especially for the 99.9% of the people that are out there that have no awareness of security. So it's important for new .NET applications to start making use of the hashing and cryptographic algorithms that exist. A little bit later on, we'll get into some of the details of that. Okay. And just to pound this again, I don't really care what authentication method you use. It's best to use the most secure ones possible, but if you do not establish a cryptographic session before you authenticate, then you're wasting your time. That's information leakage. Always create the cryptographic session before. SSL, or whether you're doing your own key negotiation, own tunneling for TCP, you have to do it before authentication. In truth, this will decrease performance. Obviously, there's quite a bit of work in a key negotiation system to establish that session. But authenticating before just means that all your authentication system is being sent out into the wind. And how many people here would say support third-party, what do we call it? Third-party key escrow. That's the word escrow. Third-party key escrow with some corporation that you don't know. None? No one would trust them? So how can you possibly trust the administrator working at the ISP that you pay $20 a month to sign up to? Do you know him? There's a lot of assumed trust on the network, and you just have to figure that, yes, our packets are routed through XISP or YISP. They wouldn't do that. They're good people. No. You have to always establish cryptography before. You never know who's watching the network. It may not just be hackers. It could be an internal disgruntled employee that just wants to pick on somebody. So large bit hashing, large bit encryption, both web and TCP applications within .NET, you should do it all the time, period. No questions asked. Is anyone here doing this currently? Good. Okay, using certificates. Right now, like as an example with SSL, the first thing you do when you establish your cryptographic session, the server attempts to actually prove to the client that he is the client. We should be doing this several steps better. You have a .NET app. It's so easy to create a certificate. All you have to do is create your magical public and private key pair. Guess what? It's also 2 lines of code. You say, declare this guy, this RSA crypto service provider instance. You pass in the bit size of the keys that you want created. It generates them. Then you can immediately pull the keys out if you so desire, store them, do whatever you want. The encrypt and decrypt function, it's right there. You just create the key. Oh, encrypt this data. It's so simple, and yet people are still relying on other people's implementations and other people's ways of using certificates. All that you have to do is generate your public and private, take some data that you want. You look at the X.509 RFC and different RFCs for certificates. You have some fields of information. You attach your public key. You sign all of that data together, attach your signature. You now have a certificate. You should be creating custom certificates for your clients. A lot of remote access systems now actually have smart cards. They give their users smart cards, so they have a personal certificate. So when they remote access in, it's a way for the client to prove who he is. Going to this type of a architecture will help reduce, in all cases, hackers gaining access to your system. Because right now it's just, oh, you can connect to my system because, well, you're on the internet. And it should be the moment you connect to a place, oh, server prove who you are, client prove who you are, before we even get to the entering your username and password. Smart cards is a really nice way to go, obviously, because it's something you have. It's like your keys for your car. If they're missing, you say, my keys are missing. Oh, my car's missing too. You call the cops. You know at that moment that there's a problem. Yes, there's definitely the possibility of putting a smart card in a system and having a hacker have a backdoor or Trojan in there that actually grabs that information. But something that you have is definitely added with something that you know, better to use for authentication. Okay, key distribution from 2 sources. If you go right now to some site that uses SSL and you get a dialog that says, hi, we have a new certificate. This certificate is trusted by VeriSign, et cetera, but they put a new certificate in there that you don't necessarily trust personally. How many people here just press yes? A couple people maybe. If you weren't in security, if you were one of the 99.9% people out there, the people that are using the systems that we create, how many of them do you think will press yes? Half? Most of them? People are just not paranoid enough out in the world. Man-in-the-middle attacks against these type of situations are prevalent. I have personally seen several SSH 2.0 using that. You connect to somewhere and, whoa, I mean, someone actually tried a man-in-the-middle attack against me, and you could see the certificates were different. This is very interesting. So certificates, you should create them. You should also give it from 2 locations. If I go to the web server and it says, hey, you have a new certificate, I should immediately be able to FTP to a different site that you own that takes a different route on the network. So geographically, meaning that that might be possible, might not be, but most likely the clients are not going to be able to, or the hackers aren't going to be able to man in the middle 2 specific locations all at one time. Obviously, this would be known that you were doing this, so they could try that, which is why you add the 3rd step, which is certificate verification phone number. It would be really nice if I went to the website and said, I have a new certificate, do you want to trust it? Well, this is where I store all my banking information, my credit card numbers, account numbers. Wait, I'm about to log in with this. I don't think I'm going to trust the certificate. No. Dial a number that, sure, I guess the phone number itself could be man in the middle, but you take extra steps for this. I dial the number and on the other end an answering machine picks up, or just some type of notification that says, hi, you've reached X Bank's certificate verification. It is this, and it tells you the signature, the MD5 hash, or something of the certificate. So if you're really worried about it, you can validate and give multiple ways for certificates to be distributed from your .NET application or from your server, depending on what your function of your application is. Certificates are very useful. They just use cryptography to allow people to identify who they are. we can mitigate and monitor a lot of penetration and bypassing of authentication systems if we do this. Okay, a note on single sign-on. .NET Passport, this is just a URL to some of the problems, exposures that has had. Something about single sign-on, I just wanted to bring it up since I was talking about authentication systems. This is the definition of transitive trust. If I authenticate to you, and that all goes well, your friend is just going to trust me because I authenticated to you. It's third-party trust after you go to a different location. Now, specifics of .NET Passport based on the fact that when you want .NET Passport on your site, you have to implement, you have to work with Passport. And there's cases where you could easily make a mistake, and then even though Passport may be secure in this way, your implementation and how you actually work with it are not. So it's important to maintain a consistent security, and having people, other people, third party, look at it, make sure your implementation of that is secure is good. So of course the hacker's problems with this, the hacker gets in through your web application. If you're using Passport, they could potentially have access to more systems than just that one if you're actually passing credentials from system to system and allowing transitive trust. Adding certificates to this type of a thing would definitely be beneficial. Adding what you have. Okay, and I'll finish up the authentication boring part with hacking the client. It doesn't matter what you use to authenticate to where. Most likely, your machine sitting at home is going to be 10 times more vulnerable than your nice machine at work that the IS department always beats you down about making sure you have patches, et cetera, et cetera. Everyone knows in the hacking community that if I want to get into that huge corporation, I'm not going to go to the front door and knock and walk in and try to do something. I'm going to go to a third-party vendor and his remote access client, and he also works here, and okay, I'm going to try to get in there, I'm going to hack that, and I'm going to slowly work my way up, and perchance I'm going to see some credentials somewhere that allow me to get into the back door. If you were at lunch when Dario was talking about the hacking group that the EECTF Foundation based out of Italy helped track down with German and US, and all these people went through this huge process to catch these 14 hackers. It was very specific how they did their work. They got into a machine using 0-day, and then they used that as an attacking point, and they went to wipe the machine after they performed their attack, and they walked away from the scene. If your .NET application is sitting on that box, you may not think, okay, I can't really stop an exploit at the IIS level or at some other level. Sure, you can't stop that from happening, but you can make it so that your system and your information, your credit cards, are in fact secure. Okay, hacking client, bandwidth for everyone. I have a friend, quick story, who decided they were going to go camping a few weeks ago, and I have a friend that bought some land up north of Seattle. It's like 75 miles up there. So they went up to this campsite on this land. They're camping there, and they get out their laptops, and what do you know? There's 3 access points in the middle of nowhere near where all this land was. It's really interesting, but you look everywhere, and you can drive around, and you can hack clients. Okay, so another thought, I always hear people saying, I'm not upgrading to XP, I'm not upgrading to Windows 2K, yada, yada, yada. Those people just want money. My computer does everything that it wants it to do. This is the awareness that just exists in the community. There's lots of people out there that are just happy with sitting with what they have because it's functional. And even in your jobs and your applications and everything else, whoa, what's wrong with this process? It's functional, it works. Well, it's not secure. And you just need to look at everything and say, okay, this works, great, but what's the exposures to it? And then at that point, do the due diligence to actually do something about it. Okay, hardcore authorization. Assume for a moment that someone actually does, in fact, break into your system, your server system, not into your application. So they're sitting on the box. We'll even assume that they get administrator access. How long is it going to take for them to steal all the information your application has to store? Does anyone know? Assume you're on a really huge pipe. You have a lot of bandwidth, and they're sitting there, and you have all these account numbers and credit cards and all these things stored everywhere. Is that a comfortable feeling? Do you feel comfortable that if someone were to actually get 0-day and break into that machine, that all your data is safe? Probably, maybe. Does anyone here feel comfortable that if 0-day hit your box, your data would be safe? Nobody. Okay. Then listen very closely. .NET allows the ability for you to, in code, do authorization. Now, this may be like, oh, okay, so yeah, he can't run that piece of code, or he can't access this. This also means you can do authorization against administrators. I just think a lot of people never thought of that or didn't figure it out. So you have these .NET principles, and you can say, okay, here's the security context. Someone breaks in my box, he's an administrator, great. The first step is to make it so that your .NET application, in fact, uses these principles, but also make sure that the person not necessarily isn't an administrator, but is in a specific group that your application works with on that machine. Okay. If you are doing web, there's an event where you can trap that you can actually get a .NET entity or identity from. This identity you can use to keep track. Obviously, this would be where you get the username, other information from that you can use for auditing and logging and tracking, etc. Local non-web, so if you're doing like Windows Forms application, Windows identity.getCurrent will give you that identity. And the same rules apply for both of these. Once you have that, you now have the ability to specifically, based on that identity, perform actions on that and check. And there's several things that you can check. It's actually very exciting. It's very nice. And nobody does this that I've ever seen. Is this person anonymous? If someone gets in your app or breaks in your system and starts bypassing things, ooh, they hacked in this way and, ooh, I've gone anonymous. I didn't authenticate to the system. You can check these. Ooh, I have an identity that is accessing my application. Did he somehow get anonymous access? Now, we're going to assume that your Windows system is trying to keep everybody out as well, but if they bypass the operating system, here's your .NET app going, I'm sorry, you didn't authenticate to me. You're a guest. I don't know how you hacked the guest account, but you're a guest. No. Oh, your system. Well, guess what? I don't let system access this application. You must have done some buffer overflow through here, through something that had system access to get inside that context. So absolutely not. We will not allow people that qualify as guest system not authenticated or anonymous to access the system. So you have a nice, when you have your principal, you have a nice way of performing the isInRole function, and that will allow you to say, is this person an administrator? You could explicitly say, if they're an administrator in the administrators group, now you deployed the app, so you on purposely said no administrators should have access, because they're administrators, not users of the app. You could say, if it's an administrator, something's wrong, because no administrator is supposed to execute this program or access this code in this way, because administrators have too much power. And if you're an administrator, you must be a hacker who got administrator on the box and is trying to use my app. So if you were an administrator, failure to a case. Audit, record the log, and probably at this point, with this error, you would dispatch that to a person and actually try to let someone know that an administrator is trying to log in and use the application in some way. Now, everybody trusts their system administrator, right? No? No hands? Well, basically for your application, and of course this goes back to a risk and money and how your basic company functions, you have an application deployed on a system. It is administrated. The system administrator should perform system administration tasks. The application administrator should have completely different access because they're two completely different problems. Now, most people may say, I trust my administrator enough to have access to the application, which could allow confidentiality and things like that to be released. If you look at some military things that they do, they always require two people. They kind of assume that these two people who don't really know each other, and in most situations are forbidden to actually know each other. It takes both of them to authenticate to the system before specific things can be done to that system. There is no reason we shouldn't use these same models in .NET, especially when we start applying these methods. We can sandbox our application so that if someone does break in and with a brand new zero-day exploit, they get to the application, they try to run it, they try to access it in some way, we say, no, I'm sorry, you are not in this specific group. Now, sure, if a person is on the system long enough, they can reverse engineer your application. They can say, oh, I need to be in the black hat users group. And in that case, they add themselves to that group, and maybe even remove themselves from the administrators group, et cetera, and then they will actually be able to get in and run your application. However, we have a nice way to stop even those people. When you build your application, you can say, there's system level authentication, and then there's my application authentication. Now, this does add a little complexity, but you can assume that when you deploy, the first time you deploy your application, the administrator goes in and he says, application administrator, he says, this user exists, this is his password. Obviously, things like rules and all of that, you might have to develop quite a bit of code, and manageability is at risk. But if the application has its own users that are segmented from the system, then you can sandbox authentication. And then that same hacker that breaks in, that changes his information and gets himself into a group so that he's at least authorized to execute your app, he goes and he logs into the system. Now, you have your Windows identity that's passed to you, whether you're web or local, and you can look at that and say, oh, this is interesting. This person is logging in. He's in this group. It's interesting. I keep my own internal copy of all of the users that are allowed into my system. He was not added to the application list before he was added to the system list. In that case, you can say, oh, he may be in the right group, but he's not even my list of users. And in that way, you can immediately deny access to that person, log it, and notify security personnel that someone not only gained access to the system, but is trying to gain access to your application in this way. Is there any questions on this specific part? Because I know it's pretty detailed and kind of catch-22. Yes? Yes? Sure. What you would do, the question was, you have to have a list of users for your application, obviously, and that has to be stored somewhere. And the answer to that is you could store it remotely. The best way to do it would be probably just to store it locally in a place where there's no access, no network, default network access, so you don't store it in the registry, right? You have your own place where you store that, and you store it encrypted. And the only person, that can modify that, and this is neat, in the code, you can limit the modification of that by only the application administrator. Obviously, if the system application itself is going to check that and do comparisons, the key must be stored locally. So you would probably just try to obfuscate it. You would put that key somewhere that wasn't directly obvious. Obviously, a hacker could find that key, go decrypt it, add themselves to that list, and go on. But remember that the entire purpose of this is that once the first trigger goes off, and no hacker is going to immediately go to that stage, this is the key, go to that stage and say, I know that somewhere there's this thing I have to modify. They're going to trip one of your other alarms before they get to that point. And this is where it goes back to the beginning slide of how much time do you have as a hacker being on a system. So you would store the key for that encrypted local user information for the application in some place. You would not call it secret.key. You should call it, of course, something arbitrarily, a little obfuscation, and maybe even not just have the key in there, but actually have thousands of keys in there, and then just know which one you need to pull out inside your application. So maybe that's hard-coded, maybe there's some dynamic settings, but that level of obfuscation and encryption and keeping that stuff secure and keeping that user base encrypted with 256 AES, and with your initialization vector for symmetric encryption being 120 bits for that level of encryption, we're talking about 376 bits of data difference. That's a dramatic level of encryption that no one's going to brute force anytime soon. And if you detect the attack, hey, Would you rather have 5 minutes or 3 hours, for that hacker? So if the hacker's got 3 hours, he might be able to do something, but at least if you detect it in 5 minutes, then you're good. Does that answer your question? Okay. Okay, administrators and trust, we talked about this pretty briefly. You store credit card information. Do you store it in plain text? No. You store it encrypted. Do you have a key that can decrypt that? No. This is actually something that is not followed by pretty much anyone. If you can go online, let's say an insurance company, that's a good example. You have a nice encrypted session, you go online, go to the insurance company, and you say, I actually want to pay my insurance. I want you to take it out of my account or with this credit card on a monthly basis. This, by default, means that they're going to access your credit card information, which means either they're storing it in plain text or they have a key to get in. And any place that does that type of auto payment is a target for hackers because they know the key's there. All I have to do is get in, and I will be able to, even if it's encrypted, I can find the key. That's what they're looking for. They can get the encrypted data and decrypt it and get the credit card numbers. So this is why you actually only want this type of information inside of your web app. It should only be stored by generative means and only can be decrypted when the client is there, which means the client has to log in. Part of his password hash is used as part of the key that is used to decrypt the credit card information or whatever their personal information is. Administrators in no way ever can access that unless they're sitting there and pretty much watching memory and as users access, steal their passwords. It's a huge way to mitigate administrators and other situations where people get in there. They still have to get the user's password. Only when the user is there can the credit card information be pulled, et cetera, et cetera. Okay. So we're going to take a look real quick at just how simple this is to do with the authorization. So what we have is, this is just a local Windows Forms app, and we pull out of the identity, which right up above here, we just do a get Windows identity get current. That just tells me who's currently logged into the system and executing this app. So we check, we say, okay, if the identity is authenticated is false. Here I go so far as to say, if they didn't even authenticate with NTLM, I'm not even going to let them in. So should someone hit certain bits in your registry, do different type of attacks, and force some type of landman or clear text authentication? No, you're not accessing my system. Are they anonymous? We wouldn't let them in. If they're a guest, we won't let them in. If it's system, we won't let them in. So that's just an example in processing of how easy it is to actually do that. Okay. .NET, it's so easy to do cryptography, and nobody uses these methods. So I'm actually I've got a couple simple demo EXEs that I'm going to run just to show people how much you can actually add to this. So hashing, 128 to 512 bits. If 128 bits takes a day to brute force, you store your password, someone gets all of these 128-bit hashes, you're like, we hash our passwords 128 bits even. Well, it's getting to the point in these days that that itself is not even enough. But let's assume a person can brute force a 128-bit hash in a day. If you double that, because it's a nice logarithmic scale because we're dealing with exponents and bits, 256 bits will take 2 to the 128th power days. And if you do the math on that one, that's basically 256 with 12 sets of 3 zeros of the number of attempts that it's going to take. So all of a sudden, it takes the rest of your lifetime and the lifetime of everyone else to brute force this, and all you did is change 2 lines of code to say, oh, I'm going to create the 256, or I'm going to create the 512. Now, eventually in time, with new versions, as it becomes easier to brute force things, there will definitely be added things so you can continually stay ahead of the loop. But it's important to you might as well go to the max now because processing, no one's brute forcing full 512-bit hashes anytime soon. That way you don't have to go modify your code every time something new comes out until that day. Everything that you can hash, you should hash. When you hash something, you lose the original data. All you have is this number sitting around. But a lot of times, that's all you need. For example, if you're doing lookups and you're passing your username around everywhere, and it's totally visible and everybody can see it, well, great. So now everyone knows what the username is. Plus, it's totally obvious how the structure of your application works. Take the time to use hashing type functions. Hash the username. Maybe toss some other random data in here, data that you know about. Create this number that no one can predict. You have no predictability inside of your hashing. You pass that around as the index. Even store it in your SQL database and do indexes, lookups into your database by that. No predictability. It's a really nice way to make it so that hackers have to try. And if a hacker is brute forcing your server, you better notice. If I'm hitting your server constantly, 1,000 requests a second, you better notice. You better have an intrusion detection system, or your application better have a nice else statement after that, if this happens. And that else statement better say, okay, big problem, our average user failure, authentication failures per hour is average is 50, and we just had 17,000. Your application can track that. Just add some code in the second part. Excuse me. So encrypt what you can't hash. I suggest that everything on your system for data storage should be encrypted. Yes, I'm kind of asking for a lot. There are serious performance considerations. Okay, where do I store the key, et cetera, et cetera. Generally, if it's user information, the user's password should be either the thing that allows you to decrypt it or part of the key that allows you to decrypt it because it's their information. You must keep that information secure. I'll do the demonstration in a second. You want to make hackers brute force large numbers. Because trust me, if I were to get a password hash and I see it's 512 bits, I'm going to take it, I'm going to throw it away. I'm not even going to try because I know, and hackers know who brute force things, that the bigger it gets, the longer it takes. Okay, let's look at .NET hashing here real quick. Okay, this is basically a very simple program that just grabs all of the different internally .NET hash algorithms, shows you their bit strength, and then actually just hashes some arbitrary string. So I'm actually hashing the string password here, and you can see MD5, we have 128 bits, and there's our hash. We have 160, 256, and as we get up here, we've got the nice 512-bit, really large. So it's very easy to do this. Let's look at the code real quick. Raw data, the offset and the source that you actually want to start your hash, and the number of bytes that you want to hash, and it returns a byte array of the hash. That is one line of code, and there's no reason you shouldn't be doing this in your applications. Yes. You mean the compute hash? Yes. Everything I'm showing you is in the .NET environment native. It was even there in the original 1.0 release. So, all right, symmetric key generation. Going back to the problem that you brought up about, okay, I got to store this stuff locally and I'm going to decrypt it, and so it's kind of a, what do I do with this key? How do I store it? Using password hashes as keys is a long time thing that's been done for forever. What we can do is we can actually store part of the key locally and then require the user to submit the other part of the key. And this way, if a user or a hacker gets on the system, they're not able to go, if they do find the key, to grab it and immediately decrypt all of the information. It requires the user to be online, obviously, because we don't want to actually store password data by the user. The administrators can't see the data stored in plain text. That's very important. Go ahead. Correct. 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 At that point in time, they would have to be required to make a new account. And I would assume you would be at some point where they could actually authenticate, maybe via phone or something, and say, okay, wait a minute, there's a problem. I can't get into my account. They would somehow have to prove that really was their account in some way that you trusted them so that you could erase it and then recreate the account. So yeah, it's a tremendous problem, and it could make you have a large tech support section.
So you don't really want to do this with data that really belongs to the user.
Correct.
Anything that's their personal information.
Sensitive. Yeah.
So your application still receives and log on.
Correct. Correct. Okay, I'm sorry, I couldn't quite get all of that. Oh, right. Yeah, it's very true. Did everyone hear what he said? Basically, keep all the preferences. You just clear out the sensitive encrypted data and go from there. Yes. You know, after I went over this before I spoke a while back, I tried to think of other ways to allow automatic payments to still work, but every one of them required that company to call you, basically, to then at that point be able to access the account. And all of a sudden, that seemed like a very huge information leak, because now you have a person you don't trust calling you and saying, hi, I'm from such and such a place, and why don't you give me this information so that I can charge your account with money? You just can't do that. So it is. Right. Right. And what I'm saying is that they should never be allowed to do that. They shouldn't have this automatic remove, especially when the specifics of it are that it's web-based, that you log into a web or just a TCP application, you're giving them all your information, you click a button that says, yes, keep this out of here. You know the information is stored in a way that you can access it, and it is automatically being taken out, which also means that someone else is accessing it. They have a password to decrypt it, assuming it's encrypted. And now, since there's this entry point from the internet publicly, now hackers can access that same entry point. So if you go down and you have to physically be in person at some place and you whip out your ID and you say, here, I want you to take this out every month, that's different from a hacker has very direct access to where those keys and information are. Does that make sense? All the automatic payment systems, web accessible, are unsafe. 100%, I believe that, yes. Okay, sensitive data is only decrypted in memory when the user is logged in to the system accessing the data. Straightforward. The moment that it is being used, if a person accesses the system and they're going over here, the first initialization that you do when they access shouldn't be, okay, let's go grab their sensitive information just because they logged in. Obviously, for performance reasons, it makes sense to cache user information, common queries, things like that. You cannot do it with sensitive information. The moment they say, yes, charge my credit card, it should say, would you like to use the one on file? Say yes, maybe right then re-authenticate. But at that point in time, then you pull the credit card, decrypt it, do your post to whatever your fulfillment server is, and then immediately forget and on purposely reinitialize all of that memory so that there's no password encrypted, any of that sitting around in memory. Okay, so let's look at some pretty simple generation here. Oh wait, I'm not there yet. Here we are. Okay, so this example basically just takes the AES algorithm, takes a 256-bit key, and generates it. I also create a 512-bit password hash ahead of time. And you'll notice right here, this first line is the key hex bytes. This second line is the IV. Both of these are used together in symmetrical algorithms. The IV, or initialization vector, is generally where the algorithm starts, since cipher blockchain algorithms kind of need a starting place. A lot of people will actually make this a static variable and then just use the key hex bytes as their key. What's really nice about this is that you take the password hash, generate the password hash, take as many bytes out of the password hash from the beginning, drop it down into the IV, and now my symmetrical key has two parts. And you need both parts of them to actually encrypt or decrypt any data. The key hex bytes I can store locally. Obviously, I should still obfuscate. Don't store it in secret.key. And the IV hex bytes is provided by the password hash that when the user enters his password. So this will allow you to mitigate the risks associated with storing keys locally. Again, obviously, the user has to be actually accessing the system before you will be able to do any encryption or decryption. Yes?
You said to not store the secrets in memory for very long, but to be initialized. How do you do that in .NET?
In .NET? There is, I believe, everything that inherits from object inherits a .initialize, which resets it to the initial state every time that you allocate. Also, you could just overwrite that memory. You can initialize a garbage cleanup. So I will note that is a serious performance hit depending on what you're doing. If you say, go collect all of my garbage memory.
If you're going to go through the variables, you want to be using a string builder or a byte array. You don't want to use a string because it creates a new copy.
Right, it creates a new copy every time. So,
And clearing it out will actually clear out a new copy. Not one
so for everyone, depending on the objects that you're using, it does create new copies. So be sure that you're using what you specifically said, string builder, or what was the other one? Or byte array, so that you are actually initializing that actual memory. And for almost all of the cryptographic and hashing stuff, you have to use byte arrays. So you're kind of just there already with that. Okay, encrypting server and client data. These are some rules to follow. In my opinion, this is just the way it should be done. Data that is stored on the server that is owned by the client is encrypted, and only the client secret can help decrypt it. What's really nice about this is if you start getting into the legality of containing someone else's data, it may limit your accountability in some situations. You have to accept somebody's credentials from getting in, but it is that person's responsibility to maintain their credentials. And your web application and your company shouldn't get sued because a client decided not to patch his machine or because he lost his credentials. So you can show cryptographically and mathematically prove that there's no way anyone got that credit card from your database. And that in itself is very nice. And if you start telling managers and other people who start dealing with risk for security, that's a very good thing to know. We're not going to be held accountable should this information get lost. We can mathematically show it's not going to be brute forced, and if it did get out, it's the client's fault, or the client lost their credentials. Data stored on the client that is owned by the server is encrypted, and only the server's secret can help decrypt this. Most people ask me, go ahead.
What you just said, you're probably not going to get held accountable anyway, right? And this sort of, this particular speech we had this morning about Rich Schneider's speech about, he's got one agenda.
Right.
And the credit card owner, the customer, doesn't really care if the credit card company's going to
That's true.
lost money.
That's true.
You don't really care if your Amazon.com is your credit card, you don't care that much. The only one who cares is the credit card company. They don't really have a
You know, I'll submit on that I agree with you from the financial aspect, But if you go to the extent of what if some invariant action of what happened with that credit card caused some other weird civil thing, I'm just thinking worst case that something that I'm not, can't think about happens, and someone decides to sue me because my coffee was too hot. It's that kind of a world, and I can see someone doing it, especially if your corporation has big pockets. So.
EII allows them to provide to that may start holding you accountable for not encrypting that data or not taking
It's true. People kind of don't take it too much to heart today because there's really no legal precedent, so to speak, yet to where they're saying do this or we will, do that. Oftentimes, yes. Sure. Sure. Yeah, that's very true. And the public eye doesn't forget big losses like that. How many people bank at U.S. Bank? How many people did bank at U.S. Bank? So you changed specifically because of the credit card hack? So there's an example right there that publicity will get you. For server or any type of server application, or even just a peer-to-peer system that pushes off data to a client in the case that they're just, the round-trip scenario for web, anytime you're pushing data off, that client is going to maintain that for you and return it at a later time, should probably be encrypted. There are definitely reasons to do this, especially in the case of other exposures that could happen to your server. If I'm a server application and I push data off, whether it's for a round trip or just so that the server holds on to it, so that I have less memory that I have to deal with, gives me more resources. When I pull it back from the client, I have to validate that information. I have to say, oh, I passed them off this when it comes back. There's potential for cross-site scripting vulnerabilities, SQL injections, buffer overflow, et cetera, et cetera, et cetera. If you use a large enough key and you just encrypt the data, when you get it back, you can decrypt it, and if it decrypts, you know it's valid. Now, if you were very, very paranoid, you might also perform secondary validation on that data alone, but if you're using a 256 or 376-bit symmetrical key, and you're the only person that has the key, and you generate that all the time, you just encrypt data and send it over, get it back, decrypt it. There's like a 1 in, I don't know what that is, 16 with some X number of zeros, one chance in that. Basically, you could go out here and go around and win every car in Vegas before that will ever happen. So that's another way that you can actually, potentially based on the size, improve performance. You can make sure that the security of that data you push off to the client is more secure. When it gets back, if you had to perform 65 substring searches because you're looking for specific SQL injections into your dynamic SQL, I can promise you that decrypting, symmetrical decryption, will be faster than your X number of substring searches and that type of thing that you have to do. So it could be even a performance increase at the same time as gaining that security. Okay, and we're going to look at crypto streams really fast. Slowly running out of time. This is something that .NET offers. How many people here have played with crypto streams? A couple people. I'll show you a really interesting implementation that I did, by which we actually, I do a binary serialization of an encrypted stream to a file, so that anytime I load any objects from disk, any file, no matter what it is, I'm doing a binary serialization, which is a very fast thing. It comes in, I'm sitting there, it's encrypted data, or actually I pull it up, I decrypt it before I deserialize, but it's a very nice way to ensure your file security of what's there. It allows you to globally actually apply that to every serialization of every object you have everywhere, so you can have the same security. You don't have to continually write your encryption algorithms. You can just make a nice object and say, hey, generate me a key. I'll keep the key. Don't you worry about that. Serialize this object, these objects over here. Poof, they're on the disk. They are encrypted. They are secure. You don't have to worry about someone getting at that data. Okay, so here's kind of the steps that go through this. I'm just going to jump right into the code so we can look at this. Okay, basically I have this class that is serializable. It's called user information. And what I do here is I'm just going to modify two properties, or actually directly modifying two private or public member variables. I'm storing a path and a username. So I'm just changing two pieces of data. And what I intend to do is serialize this using my secure serialized to a specific file, and I'm just going to overwrite it every time. Now at the end, the last argument to this, I went so far as to make it so that we do all our password hashing stuff and use that as part of the key. So you have to pass a password to this. This could be removed, and you could just, go look for a key on disk or somewhere else. But this makes it so I can do serialization of data that is client data, and only the client can supply this password. And so the only way I can deserialize those objects up using crypto streams is to do this. So I'm going to go ahead and make sure this file doesn't exist. Okay. So I'm just going to kind of step through this real quick. It's kind of a bit of code. So I created a new binary formatter, got my memory stream. I serialized my object into the memory stream. Go back to the beginning of the memory stream. Now I create my file stream. I hash my password, and this is kind of my own class that I can just pass right into. Okay, here I'm doing a generation of a 256-bit symmetric key from a 512-byte hash. And I'll just step through this. You can kind of see there's a little bit of code that gets this working. Once you pretty much get the block sizes and how you align the cryptographic blocks together to make sure it'll encrypt and decrypt for you every time, it's pretty straightforward. Okay. Here we create our encryptor, get my bytes, write the data right to the file stream. Then I create a new crypto stream, copy the data over, flush it out, close all my objects. It's really straightforward. And at this point in time, after serialization, what I'm going to do here, we'll look at the file in a moment, but I'm going to change the values of this object so that we see that it actually does deserialize correctly. So voila, if we look at the file, here's our encrypted specific user information settings, and all based on the password that they passed in. It's very simple, and it's very easy to do. So we're going to deserialize this. You'll notice the current object, I changed these two values, and after we deserialize, we should have a new object with the original values that were decrypted from the object that was streamed out. So very nice, very easy, and completely secure. Okay. So the last thing that I'm going to go through is distributed denial of service in .NET. It is very easy to perform memory resource starvation in .NET simply due to the fact that it has variable sizing variables. One of the biggest paradigm shift that programmers had when they saw .NET was in the past I had to take a string and I had to bounds check it everywhere. And now I have .NET and I don't need to do that anymore. And it's completely the opposite case. Nothing has changed. as far as the programmer's perspective when you get to .NET. They have auto-sizing variables, and those may fix buffer overflows, etc., but you still will have memory requirements and performance. So don't just allow usernames to be 1K. You don't need to. Keep the same stringent requirements you have in your application. The reason that denial of service actually is easy is because of defaults in the ability to create web and Windows forms. A text box, I don't know, has anyone seen this? The text box, what is the default size? Max size of data in that text box is 32K minus 1, or 32, I don't remember what it's off the top of my head. The rich text box is 2 gigs. How many people really need 2 gigs of data in your text box? How many people have 2 gigs worth of RAM on your server? A couple? How many people have 4 gigs? So if you throw up a rich text box and somehow I have the ability to send data to that, I don't ever have to push the OK or enter button. I'm just going to keep sending data, and it's going to keep going in the rich text box, and it's just going to, and your server will crash. So the web text box also has the same type of thing. You can, I think it might be 32K, it might be 64K. So your web text boxes, you might have just dragged them on your form, made everything nice and pretty. You have to go look at all the defaults for your settings and modify them merely because it's too easy to do a denial of service on .NET applications because of the way the UI interacts with the base objects. And here's just a simple example. I'm kind of taking this pretty far, assuming that a group of hackers actually purposely wanted to do a distributed denial of service. So we have a web page, a .NET web application. On the web page, we have 10 fields, maybe a registration form or something like that. We have 32K times 10 fields, and I'm going to assume that every hacker is actually going to create 64 sessions on his own. So a hacker establishes 64 sessions with the server, and yes, that is possible to do. So it does that, and this total here of all of the data that he's going to send, just him, is going to be approximately 20 megabytes. We assume for a moment that a standard, just a DSL user, this example gets insane once they have real bandwidth, but a DSL user has 120 kilobits of upload speed, bandwidth. So a hacker, the question is, how long does it take for this hacker to allocate 20 megs of data inside of different fields? And the answer is, we calculate his bits per second upstream. We determine how many bytes he can send per second, just 16K. The total amount of data this person's trying to send, approximately 20 megabytes, divided by his data rate, and divided by the number of seconds. We're trying to convert this to minutes, and it comes out to 21.33 minutes. So in 21 minutes, one hacker can have your server allocate 20 megabytes of data. That doesn't seem like such a big problem, but all of a sudden, when we do our multiplier for the distribution, we see that 128 machines, even at this slow 128-bit upload speed, can then allocate 2.6 gigabytes on your server in 21.33 minutes. Now, obviously, all this data coming in, hopefully your intrusion detection system would see that and maybe do something about it. But what is your reaction time? What is it? What's your application going to do? Can you actually react in 21.33 minutes and do something about it? Turn off that pipe, unplug that machine, try to save data that's being cached or log filed? Who knows? But it's important to know that the default for input into .NET, specifically variable length fields, must be mitigated. This is why every field should always have a set length. You should never leave it open. Remember, you can't rely on the client-side checking of that data because no hackers are going to use your client. They're just going to spoof the packets and make their own session using their own tool. So you're going to have to, on the server, every time you get, when you start to get that first request or that first post and all that data just starts arriving, your IDS should trigger. You should have filter rules. You should see it coming and immediately do something about it. Okay, so nothing has changed since the day of C data declarations. You have to define a size. And that should go from your database, where you know you have to say, this is going to be 32, your business layer, which is going to say, this is 32, and up to your presentation layer, and then also off to your client side. Everyone knows it's 32. If you see anything else, you should audit it, throw it into a log file, and notify someone because you know that it is an attack. Is there anyone here that doesn't get that part? You can always know when you're being attacked. Okay. So I'll finish up here with monitoring. The failure or success of any if statement, of any logical comparison in your application is a place where you should monitor. If anything, when you're beta testing and creating your application, it's really easy to say, oh, this failed. Look, it's in the logs. To actually find bugs in your application. The moment you go to your deployment, what was a debug log file should turn into a security log file. That's what it's there for. It says to you, this buffer overflow attempt made, this person failed to authenticate, etc., etc. Notify people, not just log files, because I can promise you when an event occurs that says, I am being attacked, if you have any early warning whatsoever, if you write it in the log file and 10 minutes later the hacker's in, you'll never see the logs because he's going to delete them. You can protect against 99.9% of the standard script kiddies, the people that are just running little tools out there. But the moment you get a real hacker, like this group that the EECTF caught on your system, the only way you will ever stop them is to know that they're there the moment they get there. And the only way you'll see that is through the standard analysis of how your system is being used. Monitoring your system, maintaining averages of use. What are my average users? And at the beginning, you may not actually be able to have the events enabled. You might be able to say, we have to sit here and let people for a month use our application before we'll have some baseline averages of what our throughput in these things are. The moment anything goes awry, you should know at that point in time, later when you enable those events, that a buffer overflow happened, someone tried to hijack a session, etc. So the summary is the security battle is definitely far from over regarding .NET applications specifically. People are still creating apps the same way you would an application 3 years ago. They're not using cryptography at all. Many cases, when they say, oh, here we have a method of actually implementing some security. Let's use a challenge response authentication system. They implement it or use someone else's, and guess what? It's 48 bits. Great, now it's going to get brute forced, and you're back to ground one. I think too many times key catchphrases are thrown around of, ooh, challenge response. Yeah, that's that cool authentication method. We'll use that. All of these things have their own caveats of what to do and what not to do. And understand that .NET really allows you to go as far as you can go in security. You can have the most secure data files, the most secure processes, and most importantly, you can sandbox your application from administrators and other people. So you can have a nice application sitting there. Script kiddie gets an IIS vulnerability and gets in. Guess what? They may find a file that looks like it's encrypted and download it. And yes, that may have been some credit card information or something else. But guess what? They're never going to brute force it in the time that we're all alive. So that's where people need to go, securing that information, making sure your defaults, of course, for specifically .NET stuff are set correctly. Mitigate what you can, monitor what you can't. It's as simple. When you start dealing with risk assessment and you say, let's say for a moment that you can't actually encrypt that credit card information, then you should in some way monitor every access to that credit card information and log it and keep track of it so that you can then take that data and probably that gets offloaded or broadcasted to a logging machine or in some way. Now you can audit the monitored data and say, ooh, we had an out of bounds. We had a person from an external IP or this or that accessed said file or said subroutine, and from that knowledge, we at least know something weird's going on, so we can go say, hey, there's a problem. We think someone might have your credit card information. So never use a technology or process that you cannot monitor or mitigate. These are always your two choices. You're either watching it to make sure it doesn't happen. That's what IDS systems are for. We have to watch all of this weird packets that show up because we can't stop them from showing up. We have all these ports open to the world. We're asking everyone to connect and use our services. So this is the time where you start putting monitoring into your application. You can do it. You can say, oh, wait, I'm running out of memory. That's odd. This case is happening. That's out of bounds. notify a person immediately, email fires off, someone pager goes off, they run in. You might just have stopped a serious intrusion, and if it's a really evil person, you could even lose something like an entire domain, lots of data. Need I go on? Okay. Force all hackers to brute force. That's all you can do. You can assume that they probably will, if they ever exploit your system, steal all of your data. So all you can do is make sure that they're never going to be able to brute force it. If you have to use less sized bit sizes, if you say, oh wait, I'm working on such a machine, I'm running Linux or this other thing, and for some reason I have to use this bit size, at least understand and accept the risk from that. Based on what the data is you're storing, you should use a larger bit size. If you're using something a piece of data that goes, isn't important after a week, then look at the current statistics out there, go to the RSA Labs pages in different places and say, what is the current speed at which this thing can be brute forced? And then use a lesser bit size. Say, oh, this can't be brute forced in a week, so we're going to go to 176 or something like that because the performance is better. So there's always choices you can make to limit and try to give yourself some performance, but regardless, it should be encrypted. Establish secure tunnels before performing authentication. Once someone has any credentials, obviously that's all they need. Then they're in the system, and now they're at the system level performing different types of attacks and privilege escalation. Clients are the targets. I'm not going to attack any corporation head on. So understand that all of the low-hanging fruit, as people call it, that's where the majority of attacks will happen. And in that case, trust will then be exploited up, which is why you can never have transitive trust. You should never explicitly trust any person because they tell you, I know him or I'm from him, etc., etc. Force all your remote access personnel to be as secure as your internal servers. It's that simple. I know that lots of people have to remote access. I do it as well. Really good VPNs, keeping people online as far as, are you patched, doing this? And you probably make some type of punishment on the other side if you ever catch them not locking their machine before they go to lunch, these type of things. I know that it is very annoying at times because, you're always trying to do all of this, and it kind of creates a paranoia of, well, these people could do this, these people could do this. All you can do is the best you can do within the money and risk factors that your corporations allow you. And 5 minutes early. But that's all I have. Do I have any questions? Okay. You're welcome to... You're welcome to grab me offline if you want to chat about any of this or anything else. Thanks.